Good afternoon. This is Max Stella speaking to you from Wausau, Wisconsin, the home of Marathon Electric Manufacturing. We today are going to talk about motor basics, and this is definitely going to be a very basic explanation of not so much how a motor works, but why it works and how you would use them and how you would apply them. The idea is to understand, hopefully, when I get done with this, the concepts, the terminology, and other things of a motor to enable you to better be able to specify a motor in an application for your customer's needs or the end user's needs for that matter. In the converse, it will help people go backwards and tell the motor manufacturer what it is that they're actually looking for in a more accurate and timely manner. So, to get real basic, we start off with what is an electric motor? An electric motor is an electrical mechanical device that converts electrical energy into mechanical work. Its rotational motion is a result of the laws of magnetism in which light poles attract, and light poles repel. That's a lot of words, but it's basically based on rotational magnetic theory. And who invented this concept? Nikola Tesla, a very brilliant man, invented the induction electric motor in 1888. We still use the same principles today. Anybody who does any studying of wave propagation through any medium has to study Tesla's laws because he enabled us to make a very intensely precise and complicated process into a very simple, practical application of an electric motor. We have a lot of different energy in the world today. Atomic energy, solar, wind power, fossil fuel, all kinds of different kind of energy producing devices. However, most of them are used to produce electricity because they are not used to do work. They're used to produce electricity and let electric motors do the work. So the concept here is it's not new technology. Of course, it's been improved on, but it is very common, and this is why it is very common. Electric motors are readily available. They're easy to install. They're rugged and reliable. They don't usually fail. They're maintenance-free. They're very efficient, which is always an interesting concept these days. And they all come at a reasonable cost. Now, you don't have an atomic refrigerator in your house. You have an electric. You don't have a wind-powered furnace. You have an electric motor driving these. So you will find these things everywhere. Residential in your home, commercial in your office, industrial in your factory. Motors are everywhere because of the concepts we just talked about and the features that they have. Today we're only going to be talking about a specific type of motor, AC induction motors. And they're divided into two categories, basically, single-phase and three-phase power-sourced motors. This is a picture of the waveform. Again, we're not doing engineering 452. This is just a picture of the three phases of a three-phase system. Notice that they overlap one another. And the concept is when one of these waves is positive, the other two in the same time are negative, but one dominates over the other. So what happens if you were to try to vectorially add these things together, which is not possible, but the concept is these waves together will produce a wave that rises and falls and moves along with time. How many times the waveform rises and falls is a term called frequency. Another word for frequency is Hertz, named after a German physicist. So that's what a three-phase looks like. This is a single-phase waveform. You notice whenever there's a peak, there's no valley at the same amount of time. And the wave, therefore, rises and falls, but it does not travel by itself. It rises and falls. In order to use single-phase power to make a motor, we have to physically move this wave off of its dead zero point. You see that at 0 degrees, 180 degrees, and 360 degrees, this waveform transitions and goes through 0 3 times. So every minute part of a second, the waveform is going through a 0 point, which cannot produce rotation. So this wave we're talking about, we're back to three-phase now. How fast is this wave going to move? Well, it's going to move based on the frequency, the rise and fall of the waveform, how many times, how many cycles per second, and the number of poles that we wind our motor with. We're going to capture this wave. We're going to take this wave in the ocean, we're going to capture it into a circle. We're going to create a bunch of north and south poles, magnet poles, in that circle, and that wave is going to travel around the circle at the speed called synchronous speed. Then we are going to put a rotor inside the stator. Stator is the stationary part that holds the windings. Rotor is the rotating part. We're going to put a rotor in the middle of the wave, and the rotor will try to follow the wave in the circle, thus causing rotation. Okay, there's two speeds we want to talk about when we talk about motors. Synchronous speed, which is the speed of the wave, and the motor speed, the actual shaft motor speed, which is different than the synchronous speed by a factor called slip. The motor speed is always less than the synchronous speed. Why? Because the shaft is always being held back by a concept called torque. Torque is a turning effort. Anytime you turn anything, it takes some kind of force and a distance. It's an effort to turn it. So, when the motor is producing torque and the load that it's connected to is demanding torque, those two will meet and balance at a speed slightly less than the synchronous speed of the motor, and that's where the slip comes in. That's what the slip concept is all about. It creates torque and it requires torque. So the machine torque we want to talk about, before we talk about the motor torque, there are basically three kinds of classic machines here. The third one, machine C, is not as common, so we will concentrate today on the first two. Machine A is a variable torque load, and a variable torque load, you can see by the chart on the left, that the torque increases exponentially as the speed increases. That is why it's called a variable torque load. A typical application of a variable torque load is a blower or a fan. If you turn the fan blades when the fan is off, they're very easily turned with one finger. But as the motor turns the fan up to speed and air starts to blow from the fan blades, now you have power, and you can't put your finger in it, obviously. The second type, machine B, is what is called a constant torque load. You can see from this curve that the constant torque load is not speed dependent. It does not change with the speed. That's because the load is always impressed on the shaft at the same value. A typical example would be a conveyor. If you put weight on a conveyor of 100 pounds, the motor has to move the 100 pounds. It doesn't matter what speed it moves it, it's always 100 pounds. Okay, so that's a constant torque machine. But the speed is very important because speed times torque is horsepower. And horsepower is how we measure the output of a motor. It's simply divided by a constant, very simple formula, but something you need to remember, speed and torque is horsepower. Okay, so now we're going to take the electrical power from the utility, we're going to capture it into our motor, we're going to get our rotor to rotate, we're going to hook a load to it, and we're going to make horsepower. There is no possible way, unless you defy the laws of physics, to make the horsepower value be exactly equal to the input value supplied by the utility. There's always some loss. The loss is expressed as efficiency, not the loss, but the ratio between the work done and the work in is expressed as a fraction, which we usually use as a percent, and that is called efficiency. How well does the motor do this conversion? Because of the laws of physics and the laws of conservation of energy, we cannot lose power. Our energy has to be conserved. So, if we're not converting 100% of this energy into motor horsepower, what are we converting it into? And the answer is heat. That's the other form of energy. When a motor does work, just like you and I, it will get hot. Three-phase motors usually have mandated efficiencies from the federal government. Now, here is a speed-torque curve of a three-phase motor. We talked about speed and torque in the concept before. Torque is on this horizontal or vertical, speed is on the horizontal. When the motor starts, because the wave will always start and run a three-phase motor, it will start at the point where the cursor is. Now the rotor is trying to accelerate and catch up to the synchronous speed, which is way at the bottom. And it just keeps accelerating until it gets to that point right there. That point is where the motor torque is equally balanced by the load torque. And now the motor cannot accelerate, it simply runs there, and that speed is slightly less than the synchronous speed, the difference being the term slip. Polyphase motors can always start, they know how to run, they don't need any help. They are the brute of large commercial and industrial applications, and they are a very efficient way of making this conversion, much more efficient than fossil fuel engines, for example. We describe our polyphase motors by their design type. These design types are called Design A, Design B, and Design C, Design D. They are defined by NEMA, which is the National Electrical Manufacturers Association, and it really basically lends itself to the shape of the speed-torque curve. The shape of this curve changes depending on the design, A, B, C, or D, that we have. They're widespread through the industry, and efficiencies are usually mandated, as I said before, unlike single-phase motors, which we'll get to in a minute. So this is a little busy chart, but it just kind of says, okay, here's the machines that use these design-type speed-torque curve profiles. The absolute standard is Design B. Those are general-purpose motors, and those are the ones that you normally find in most applications. A, C, and D are special. We won't get into it immediately now, but just that you know that they are different because of the shape of their curve. Now we're back to our friend single phase. It rises and falls. It can't travel. How are we going to make this wave go around our stator with only one phase? Well, the way we do it is we artificially get this thing to move off of these dead center points by using an auxiliary winding, which is usually called a start winding. The analogy would be the starter in your car. You turn on the key of your car, and lights go on and bells ring, but the engine does not start until you turn the key farther. When you turn the key farther, you engage a starter motor to start your engine. That kicks the engine over. Once the engine fires, it can run, but it can't start by itself. It's the same thing with single-phase motors. They will run, but they won't start. Here's why. Here's the speed-torque curve of the motor with only the one winding in it. You notice it will go all the way down to zero speed and zero torque. It will not start. It cannot start the rotation. The auxiliary winding, the way it's placed in strategically in our motor, causes the wave to get off dead center. It gets started, it accelerates up, goes through a switch point, which we're going to talk to in a minute, and now it can continue to run. So once we get it started, it will run. This switch point is what happens when you turn the car key on to start the engine and then you let it go. It goes back to its normal position. The start motor is disengaged from the system. That's what this switch point is. And it uses a device like this, if I can show it to you. It's called a centrifugal actuator that rides on the shaft. Now, there are more mating parts to this, but this is the secret of this switching point. There are weights on this thing with springs holding the weights together. As it spins in our motor, the weights begin to pick up centrifugal force, like the force of the child on a merry-go-round. The faster it goes, the harder it is to hold on. That's centrifugal force. Once that centrifugal force exceeds the force of these springs holding these weights together, this thing will snap open like that, and when it slows down, it will snap closed. Now, I have a cutaway motor here, and I'm going to attempt to show you this in real life. This is a cutaway motor, the switch is, take my word for it, the switch is in the back here, and I hope you can hear this. When I engage this motor to start, the rotor will accelerate. You will hear the switch click open. Now it was open. You can see it spinning in the back. When I shut it down, it'll close, waiting for the next time it needs to start. That's the secret of most single-phase motors, and that's why the speed-torque curve looks like it does. Most single-phase motors are not called design A, B, or C. They're actually named for the way they are started and how much torque they produce. One of the most common is called a split-phase motor. Split-phase motor have moderate starting torque, and the switch is involved in taking the start winding out of the circuit, which we'll see in just a minute. And they are usually used for variable torque loads. Remember, variable torque are fan and blowers that are easy to start, so you don't need a lot of starting torque. And the split-phase motors are used in furnaces, air conditioners, water circulators, light pumping applications, fans, and blowers. Here is a schematic of what I'm talking about. You can see that the starting torque is very low, almost the same as full load. This would not start the constant torque load because it doesn't have enough starting torque to get the rotor to accelerate. But it would a variable torque load, which would start way over here. Here's our main winding only, and here's our auxiliary. This is the starter. This is our engine starter right here. This is what gets the motor to get off dead center and start rotating. The switch is located right there. The switch opens. The motor continues to run on the main winding only, and the auxiliary winding is out of the circuit, and it's going along for the ride. Okay, so what if we have a constant torque load? What if we don't have a variable torque load, and we need a lot of starting torque, and I can't get it out of the split-phase motor? Well, this other single-phase motor we designed, which is more of a general-purpose motor, is a capacitor start motor. Capacitor starts utilize a capacitor to give the motor more torque at starting. Here's a picture of them. The capacitor in this motor is in the side box. In this motor, it's in a little housing that we call a doghouse or a capacitor cover, and that's where the capacitor is. This is what a capacitor looks like. It has physical properties and electrical properties that I'm going to explain in just a minute. Here's a speed torque curve. Notice the big amount of torque we have here to start the motor to accelerate. We still have the switch, which is over here, but we've added this device, which is a capacitor. So how did that capacitor get all this curve to move way over there and give us torque? Well, this coil, electric motors have coils. This coil has impedance that is frequency sensitive, and that impedance is inductive because it's a coil. The capacitor has impedance also. Impedance means it restricts the flow of power, like a garden hose. The longer the hose and the smaller diameter of the hose, the more restriction you have. That's called impedance in electric motors. Capacitors have impedance also, but theirs just happens to be opposite and inverse to inductive impedance. So this capacitor negates that, this impedance negates that impedance, gives us more pure power, and we get more starting torque. The simple example I can explain is a radio. By the way, also invented by Nikola Tesla. Don't believe the Marconi thing. Nikola Tesla invented the concepts for the radio also. The radio station is broadcasting at a given frequency by its call letters, 95.5, 105.6, whatever the call letters are. The radio has a coil, looks like that. It has a coil that's trying to pick up that signal. But because it's frequency sensitive, that impedance is so high that there's no way it can pick up the radio station with any power. So we put in a capacitor. What's the capacitor? That's the dial on the radio. It's a variable value capacitor. You turn the dial, change the value of the capacitance until it negates this inductance at the correct frequency, and that radio station plays in your speakers. So all we're doing here is tuning our radio for 60 hertz because that's the frequency we have. There's another concept in AC motors, single phase, where we put a second capacitor in called a two-value motor. This is a motor that's specially made to get more performance out of the running end of things, not the starting end of things. As you can see, the speed torque curve looks very similar to the previous one. However, the switch only removes one of the capacitors, the other stays in the circuit all the time. Now our auxiliary winding is not going along for a ride, it is helping us in the run condition produce better efficiency, lower amps, and more horsepower really. And that's why pump people really enjoy this motor, because they can get more horsepower out of the same size motor on their pump than they could with the previous one. Okay, the last one we want to talk about is a permanent split capacitor. This motor type was developed primarily for the air conditioning industry a long time ago, and it is the workhorse HVAC market today. It's called a permanent split capacitor because the capacitor in the motor, there's examples of what they look like. The capacitor in the motor is permanently in the circuit, like the previous motor. There is no switch, however, in this motor. So this auxiliary stays in the circuit all the time to help the motor run at higher efficiency. What does it do for the starting? It does inverse to what you would like it to do. It does not produce a lot of starting torque. That's by the nature of the beast. It is designed to help the running condition, not the starting condition. But we don't care, because we have a variable torque load which starts here. We don't need starting torque. And when we accelerate, we get good running performance. Air conditioning, furnace people love this motor. That's what it was invented for, because it's reliable and it is has no switch to fail. Air conditioners and furnaces switch on and off a lot of times. They cycle on and off depending on the weather. The more times you actuate this switch, the more time it clicks. It's mechanical. It will fail eventually. It only has a certain life. So it is eliminated in the PSC. Here's a chart that compares one motor to the other and compares the single phase to the three phase for your further explanation and study. Okay, so now let's get back to the other concept we have to worry about. The first thing we had to do was create rotation. We did that. Then we had to be able to make enough torque using the concept of slip to drive a fan or a pump or whatever it was that the customer wanted to drive so we can produce the horsepower. We did that. But you remember we have efficiency. And now we have this heat situation. We have to deal with the heat. We have to get the heat out of the motor somehow. One way to, the way we do it is by various enclosures. The first enclosure we want to talk about is an open. Now, motors either have openings in their frame, like this one does. You can see the openings if I slide it over here enough. It has openings, or it does not. It's either enclosed or it's not. So an open drip-proof motor is the most common open motor on the marketplace. It derives its name from the fact that the ventilation openings are so constructed that drops of water or particles cannot enter the motor if they're dropped from 15 degrees on either side of vertical. That's why it's called drip-proof. If the vent holes were all the way around the motor, then it would have to be called simply open. It could not be called drip-proof. There's a fan inside the motor that draws the air in. It draws the air in these openings and blows it out other openings. So the room air goes through the motor and out. That really takes the heat out and is a very efficient way to cool the motor, obviously. However, sometimes the environment that the motor's sitting in is not conducive to be inside the motor. It might be wet, it might be dusty, it might be caustic, it might even be volatile. So we have to sometimes make motors non-ventilated and totally enclosed, And totally enclosed motors come in a lot of varieties. First one we want to talk about is a totally enclosed non-ventilated motor. There is no ventilation whatsoever. So you can use this motor in an environment that's not conducive to go inside, but it has to be designed so that the heat will just convect from the frame. It's not anywhere near as efficient way to cool the motor. On an enclosed motor, the most efficient way is to put the fan that we had inside the previous motor on the outside. Now, at least we can blow air along the case of the motor, the frame of the motor, and try to wick the heat out from the center. We can't get it inside, but we can certainly blow it on the outside, and that will cool the frame and keep the heat from damaging our motor. We can have a totally enclosed air-over motor in which the customer would supply the fan if we were driving a fan, and that fan would supply the air over the motor. Now, sometimes the environment that the motor in is hazardous or hostile or explosive. In that case, we use a very special enclosed motor called explosion-proof, which is built to very demanding standards mechanically. Parts fit very, very tightly, and these motors are intended to not explode the environment that the motor is located in. It could be gas fumes, it could be dust particles, whatever it is that is explosive. The National Electrical Code, the National Fire Protection Act, UL, CSA, all have standards on what it takes to make this motor operate. Here's a suggestion. You should never specify an explosion-proof motor for your customer's application because the customer has to have some authority that is in charge of this application's installation and startup. And that's the person who does the specifying. So you get the information from them, then we can supply the correct motor for the correct application based on the end user's requirement. Sometimes we have a situation where the motor is in an environment that we need to wash down, especially in a food processing plant or a dairy or even in a car wash. We make motors like that called washdown duty motors. They are totally enclosed. They're also sealed up. All the openings on the shaft, the fan, are sealed with seals. The gaskets seal the conduit box, which is the connecting device from the rest of the motor. Basically, we have two types at Marathon Electric. We have the WashX motor, which is a white one. It's painted white, and it is for not such demanding applications, but they are washed down. The white paint is not only a rust preventative paint, it is non-toxic, so it can be used in food processing in case any of the paint were to be flaked off the motor. The brute motor in the washdown duty is the SXT, which is all stainless steel. All the parts are stainless steel now. You can wash that down with some caustic soaps or whatever that would harm this motor and won't harm that motor because it's stainless steel. Okay, now we have to bolt this motor down. We have to hold the motor in place for the customer to use it. So, several ways we do that. One of the most common is called a rigid base. Let me bring my motor back in here. The rigid base is that foot thing there with the holes in it that's welded, bolted, or cast into the frame. Therefore, it's called rigid. That's what you bolt the motor down, to a base plate, to a table, to the floor, wherever you need to, and then you come off the drive shaft over here to do the business end of your work. Okay. There's also a type of motor mount called a resilient base mount. Now, let me turn my motor back on and I'll show you why these are used. Here's my motor. We're going to turn it back on. Okay, there's our motor. Now, you can barely hear me talk over this motor. If this motor were to be on a furnace or something in your house, bolted to sheet metal, you certainly wouldn't want to hear that noise all the time. So we use a thing called a resilient mount. This is a resilient ring like this. It's rubber on the inside, metal on the outside, attaches to our end bells. In that form, you can see the ring, and the base would attach to the rings, and that will isolate most of this noise and vibration the motor makes from the place it's mounted to, and that's why they're used in that situation. Sometimes we don't want to mount the motor by its foot. We want to mount the motor up against a bulkhead or into a gearbox or whatever. So we use a flange mount, this is a typical flange mount. It's called a C-face. It's hard to see, but these holes are tapped, so you can actually bolt this motor right to a wall or to a bulkhead or to a gearbox. And you wouldn't need the foot. You can have the foot, but you wouldn't need it. D-flange is another way to do that. N or M flange is a similar way to do it. I don't have an example, but this motor has a flange on the front that has ears on it that you can mount to your device. This type of motor, this type of flange is used on oil burner furnaces, and in recent years, auger drives in the poultry industry like this type of mount to mount to their auger gearbox. Sometimes we just extend the bolts that hold the motor together and let the customer use those bolts to mount to his bulkhead or his wall or whatever he has. The next concept we want to talk about is the frame size. If you cannot work in the motor industry, buy motors, sell motors, or manufacture motors for very long until you get hit with the term frame size. And what does it mean? Most people know that the frame size, the larger the number, means it's a larger motor. But how did we ever come up with the number like 56 frame or 324 frame? I mean, they make no sense unless you know the concept. They do make sense. The idea of the frame size is for the motor manufacturers to manufacture specific mounting issues with the motor, the shaft diameter, the foot, the holes in the feet, the holes in the C-face, all to the same dimension. The idea then is brand X motor and brand Y motor can be possibly interchangeable because they will mount the same. And that's the reason they do that. Now, people that manufacture widgets don't know what motor is going to go on the widget. They just make widgets. So they make the midget fit the frame size of the horsepower they need, and they expect every motor manufacturer's motor to fit that, and most do. That's what it means. But how did they come up with the numbers? Well, there are 2-digit frame numbers and 3-digit frame numbers. Now, in the computer industry, in the computer side of things, this 2-digit frame is usually preceded by a 0 because we have 3-digit frames and we need a placeholder, but that's not the frame size. Frame is 2 digits, 48, 56 are an example. If you take the 42 frame, take the 2-digit frame, divide by 16, how many 16ths of an inch is that? 3.5 inches. That means that in a 56 frame motor, the shaft, center shaft height to the bottom of these feet is 3.5 inches. That's what that means. In a 2-digit frame, it's divide by 16. In a 3-digit frame, take the first 2 digits and you divide by 4. Example, 365 frame is 36 divided by 4 as a 9-inch shaft center. Now, if you were out in the field and you had to replace a motor and you weren't sure what size it was because you couldn't read the nameplate, one way to tell what frame it is to measure the shaft height because that'll give you a clue, at least. Anyway, back to our friendly, not so friendly heat situation. We know that we can make horsepower. We know that we can drive the load. We know that we can't do it 100% efficient. We know we're going to get hot. We know what kind of enclosure we have to have because the application demands that. Now we have to make sure we design the motor to stay within the allowable insulation class of the materials that we use in our motor. Class B is a very typical insulation system used in drip-proof motors, simply because drip-proof motors normally run cooler because they're easier to cool because their cooling is more efficient. Class F and Class H, the higher temperature ones, were developed after the 60s when man was in space, when new polymers and plastics were invented, and they have a higher temperature rating. We cannot exceed these temperatures in the application. Otherwise, we lose the ruggedness of our motor. Every 10 degrees we go above this temperature will theoretically cut the motor life in half. 20 degrees over would cut it in fourth. So it's the total temperature that the insulation system cares about. Doesn't care where the heat comes from. Just knows that if you get too hot, I'm going to fail. And there are 3 elements typically we deal with in the motor issues. First one is the temperature rise. Temperature rise is the heat that the motor produces to do its job. That's what temperature rise is. The second thing we talk about is the ambient temperature. That's the surrounding medium of air, usually air, it could be water, that surrounds the motor in the application. That ambient temperature is part of the application. It's not part of the motor design. It has nothing to do with the motor design yet. The third thing is altitude. If you've ever spent any time Marathon Electric is located in the Midwest. That's fine. But if you take a trip to Estes Park, Colorado, which is 10,000 feet up in the air, it is very difficult to breathe. The air is thin. The air is thin because it has less molecules. Has less molecules, it won't transfer the heat. The motor will get hot. The higher you go in altitude, the hotter the motor will get. That's a simple matter of physics. So, the standard ambient is 40 degrees centigrade. For higher ambience, we have to make an adjustment. You'll see what the adjustment is in a second. 40 degrees centigrade is 104 degrees Fahrenheit. It was derived because that's the temperature that the specification writers determined would be the hottest temperature that human beings would like to work in. The standard for altitude is 3,300 feet or 1,000 meters. Again, goes way back, but the spec writers said, well, most of the industry in this country, especially, is located in the east and the Midwest. Not so much in the mountains. The only thing up there was buffalo, or grizzly bears. So 3,300 feet or 1,000 meters was the altitude standard is set by, and that's what we design our motors as the standard. If the temperature is higher in the ambient, or the altitude is higher than 3,000 feet, we have to make an adjustment. The only thing we can make the adjustment is the temperature rise of the motor design. Can't do anything about the altitude or the ambient. That's where the motor is located. So that's why temperature rise is used to control the temperature, total temperature of the insulation class. Now, let's talk about this part of heat. There are times when the motor is asked to do something that it's incapable of doing. It could be by accident. It could be something has gone wrong in the system. For whatever reason, motors are not very smart, and they are, to a fault, obedient, which means if you ask the motor to do something it can't do, it'll do it anyway, and it will burn up if it's overloaded. And burning up the motor is not a particular problem. We can always get a new motor, but we certainly don't want to cause a fire if the motor were to burn up. So we use thermal protectors, especially in single-phase motors, for that purpose. Thermal protectors will generally protect the motor, and its intent is to prevent it from causing a fire. There are basically three types that are used in the industry. First one is what's called an automatic reset. It has a thermal disc in it. That's the silver thing, if I can get it turned right, and this light. And it has terminals on the back to hook the line leads to. These things are both temperature and current sensitive. All right? So if there were an overcurrent situation or an overheat situation, this thing would snap open, similar to our other device that snapped open, and take the motor off the line and not cause a fire. The second type is a manual overload situation. This is the same thing. It has a thermal disc buried inside here in connection to the lead, but it has this big red button, as you can see. What does that button do? The manual reset means that once it trips and the motor cools off, it will not restart unless somebody physically pushes this button to resnap the disc. That's used when there are possibilities of an unexpected start causing a hazard to a human being or the building. Like, for example, a saw. You certainly don't want to be messing around with a saw and have it accidentally start. Another typical example in your home would be your garbage disposal. You put a rag or a spoon down the garbage disposal, it overheats, it overcurrents, and it trips this button. This button is usually located underneath the sink, way in the bottom of the unit. So you have to physically go down, get your hands away from the garbage disposal, and go down there and start pushing on this button to get it to reset. The concept is your arms are not long enough to still dig in there to try to find the rag when you're trying to press on this button if you forget to turn it off. Otherwise, you may cut your hands off. The third type is a simple switch like this. It's called the thermostat, used primarily in three-phase motors, but sometimes in single-phase motors. This one is not a line-interrupting device. It is simply a thermal switch. It clicks open inside, and these leads become open. The leads are connected to the controller that says, I'm getting hot, get me off the line, and it trips the motor out. Usually the motor starter, sometimes your control panel, whatever. Okay, that's all well and good. We have everything we need. We have the right motor for the right application. Everything's fine, except my customer is really concerned about his process control. He wants the motor to have more than the speed that it does normally. He wants to have variable speed. So how do I accomplish that? Well, the three things, if you remember back on the slides, there's three things that determine the speed of the motor. There's the frequency, the number of poles, and the amount of slip. That's the only three things. If you have a motor that has a certain amount of poles and a certain amount of slip, and the utility supplies the frequency, you're only going to have a one-speed motor. So what do? Well, in fan loads, we build motors like this. We build multi-speed PSC single-phase motors. We put multiple speed taps in. What the speed taps do is strengthen or weaken the motor that changes the slip. It makes the motor stronger, faster, or weaker, slower. Kind of like a ceiling fan. You pull the chain, you got medium speed. You pull it again, you got low speed. Okay? But I have three kind of distinct speeds there. The other thing is, the second factor is the number of poles. I can change the number of poles. I can put in a 4-pole motor and an 8-pole motor. Now I'll have two speeds. My customer says, that's all real nice, Max, but I want any speed. Any speed I want, any speed. Well, there's only one thing left, and that's the frequency. I can give you any speed by using a variable frequency drive. What is it? What does it do? It provides variable frequency power to a single winding motor. Now the single winding motor has the same poles. It's only got one winding. It's got one poles. It's going to have different kind of slip when I change the speed, but it has now the ability to change because I'm going to change the frequency, which is the third factor. It gives you almost unlimited starts and stops, changes and starts and direction. It can protect you against overheating, but the real thing is it changes the speed. Here's what one looks like. Here's what a curve of one. Most modern VFDs are what we call pulse width modulated. The electronic devices, transistors in the motor, they take the waveform from the utility, they store it on a DC bus, and they spit it out in pulses. There's positive pulses, negative pulses. The pulses have the same height, but they do not have the same width. So, hence the name pulse width modulated. Modulated means your variable that you're changing. The thicker pulses produce higher peaks on the line. Thinner pulses produce lower. Plus and minus, we are back now to a curve, just like we had before. Only this curve, and you can do this three-phase, by the way. There'd be three curves. But this curve goes up and down. It rises and falls. How many times it rises and falls per second is its frequency. With power transistors, I can give you any frequency. So what does that do to the motor? The high-speed switching can be harmful to this motor. This is a side light, so you should be careful about your insulation system. But what it does is produces a family of speed torque curves. The speed torque curves change because the frequency changes the synchronous speed of the wave. Every time you go lower in frequency, the motor slows down. Now you can imagine if you put a fan curve in here, every time it crossed one of these lines, you'd have a new speed. And you virtually can have every speed that you want, any speed. So if you have a fan load, you have to beware of overspeeds because just as correctly the motor is easy to start, it builds up speed as it runs. So if you try to go too fast, you can overheat the motor. Summary. My summary is we're going to take a wave from the utility, single or three-phase. We're going to capture it in a circle in our stator. We're going to put strategically placed coils. We're going to produce north and south poles, up and down, up and down, up and down. We're going to put a rotor in the center. The rotor is going to chase that curve around. It's going to go north. It's going to be attracted to north, repelled from south, repelled, attracted, repelled. It's going to make a rotation. That rotation is slightly less than the speed of the wave because of slip. Slip is torque. Torque is produced by the motor. Torque is demanded by the unit. Those two balance, the motor stops accelerating. We got all kinds of running situation. Now we're doing work. That work causes heat. We got to get rid of the heat. If we can't get rid of the heat, we have to protect from the heat. And that's basically it. We get rid of the heat with ventilation systems, and we get rid of the heat with more and more efficiency. And that's a basic summary of how and why a motor does work. So, motors are everywhere. I mean, everywhere. If you go in your kitchen tonight, when you get done seeing this video, start counting. Anything that plugs in and moves is going to have a motor. You'll have at least 15 of them in your kitchen. You'll be surprised. Electric knives, blenders, fans. Your refrigerator has 3 of them. It doesn't move unless you move it, but it has 3 motors in it. You'll have a vent fan for your oven. You have all kinds of motors. If you have some basic idea of speed, torque, and RPM that you can take away from this presentation, it might help you do your job a little better. That was the whole reason for having this. So, let's ask some questions. I'll pause for a second after each question to see if any of this has sunken into a motor takeaway issue. The ratio of the work produced by a motor divided by the electrical power it consumed is called what? We have work produced, we have electrical power consumed. What is that ratio? Efficiency. That's how we measure the efficiency of the motor. By the way, an electric motor of any significant size is about 3 or 4 times more efficient than a fossil fuel engine of the same size. In other words, a 50 horsepower motor is about 90% efficient, and a 50 horsepower engine is about 25% efficient. That's a fact. 3 factors that determine the motor's full load speed. We just talked about them. We talked about them all through the thing. What determines the motor's full load speed? The frequency of the power supply, the number of poles in the motors. And by the way, poles always come in pairs. You have to make a north pole and a south pole. You can't have an odd numbered pair of poles. And the amount of slip. The slip is the torque. It produces the torque and it requires the torque. So those 3 things determine the motor speed. 3 types of machines described when I talked about torque of the machine. Which one is considered the variable torque load? The one that's easiest for the motor to handle? Which one of those applications would you think? If you said fan, you would probably be correct. It's fan. Fan has a variable torque load. Easy to start, but runs with a lot of power. Lathes are hard to start. Conveyors are very hard to start. Which of the following single-phase motors does not use a starting switch? That's this switch right here. We take the start winding out of the circuit with this switch, remember. Which motor does not have a start winding that comes out of the circuit? If you said B, PSC, final answer, you would be right. Next question. Of these enclosure abbreviations, we like to abbreviate everything in our industry. What do these abbreviations mean? Totally enclosed fan cooled. What does the second one mean? Open drip proof. And the last one, as you will imagine, totally enclosed non-ventilated. Very good if you got those right. Why should the motor personnel not specify an explosion-proof motor for a customer's application? Doesn't mean we can't supply them, but we, as motor manufacturers, should not specify. And you, as customers, should not specify until you get the right information. Why? Because it's not your call. The authority having jurisdiction over that installation and startup is the person that makes this call. Now, it could be a safety engineer, it could be an insurance engineer, it could be a consulting engineer, it could be the Corps of Engineers, it could be fire marshal, it could be a city engineer, it could be anybody, but whoever's got that authority makes that call, not you. Okay. What's the distance in the center of the motor shaft extension to the bottom of the motor foot of a 324 T-frame motor? Okay, let me think what he said. 3 digits, 3 digits. Yeah, what do I do with 3 digits? Okay, well, I got 4 digits there, but the T doesn't matter, does it? No. Okay, it's 32. 32, what do I divide by? 16? No, that can't be right. 32 divided by 4 is 8 inches. That's an 8-inch center shaft motor. Very good. The temperature of the surrounding air medium in a motor's application, the air that is drawn through a drip-proof motor or blown over the frame of a fan-cooled motor is called what? Ambient temperature. It's kind of like a nice restaurant that has ambiance. It's ambient. What's the speed of a motor's rotating magnetic field? Not the speed of the motor, the speed of the rotating magnetic field that the rotor is trying to catch. What is the name of that thing? Synchronous speed. Synchronous speed is the speed of the wave. Motor speed is the speed of the shaft. Okay? What two factors multiplied together determine the motor's output horsepower? Let me think about that. Horsepower is power. What two factors, what two issues do I have to multiply together to get horsepower? It was probably the second or third slide I showed, and if you said speed and torque, you would be absolutely correct. Here we have some basic motor terminology in this appendix that describes in a little more detail all the things I talked about during the presentation for your future reference if you go back and say, what did he mean by torque and things like that. So, I thank you for your attendance, and this is the conclusion of our little motor basic theory.